Right now, two of the most destructive forces the universe has ever produced are locked in an embrace that has lasted longer than the Earth has existed. Somewhere out there, deep in the heart of a distant galaxy we may never visit, two black holes, each one millions or even billions of times more massive than our own sun, are slowly, inevitably, inexorably spiraling toward one another. They have been circling each other for millions of years, and when they finally collide, the resulting explosion of energy will be so immense, so incomprehensibly violent, that it will send ripples through the very fabric of space-time itself. Ripples that will travel across billions of light years, passing silently through everything in their path, including you, right now, in this very moment. You would not feel it. You would never know, and yet the universe would be forever changed. This is the story of what happens when two supermassive black holes collide. A story written not in words, but in gravity. Not in light, but in the warping of space and time. A story so vast, so slow, and so absolute that it makes our entire human history feel like the briefest flicker of a candle in an eternal night. And before we drift deeper into this journey together, if you enjoy long-form space documentaries designed for deep listening, for nights when the universe feels close and the questions feel infinite, please consider subscribing to this channel and leaving a like. It helps more than you might imagine, and it means that stories like this one can keep being told. Now close your eyes if you wish. Let the cosmos come to you. Let us begin. To understand what it truly means for two supermassive black holes to collide, we need to first understand what they are. Not in the way a textbook might describe them, as dense objects with extreme gravity, but in the way the universe actually experiences them. Because a supermassive black hole is not simply a very large, very heavy thing. It is a place where physics itself begins to break down. It is a boundary, a threshold, a point of no return, written into the very structure of reality. At the center of nearly every large galaxy in the observable universe, there exists one of these objects. Scientists believe this based on decades of observational evidence, confirmed in dramatic fashion in 2019 when the Event Horizon Telescope collaboration released the first ever direct image of a black hole's shadow. The supermassive black hole at the center of the galaxy Messier 87, located approximately 55 million light-years from Earth. That image, blurry and orange glowing as it was, represented something extraordinary. It was humanity's first direct visual confirmation of something that had been theorized for over a century. A real black hole, real, existing, waiting in the dark at the heart of another galaxy. The black hole in M87 is estimated to contain roughly 6.5 billion solar masses, 6.5 billion times the mass of our Sun, compressed into a region of space so small that if you were somehow transported to its edge, to the event horizon, you might not even realize anything was wrong until it was far, far too late. That is one of the most counterintuitive aspects of supermassive black holes. Unlike their smaller stellar mass cousins, the tidal forces at the event horizon of a truly supermassive black hole can be relatively gentle. Gentle enough that you might cross the point of no return without feeling any dramatic shift. You would simply be inside. And nothing, not light, not radio waves, not any signal or force known to science, would be able to carry the news of your crossing back to the outside universe. Our own galaxy, the Milky Way, harbors a supermassive black hole at its center as well. We call it Sagittarius A star, or SGR A star. In 2022, the Event Horizon Telescope collaboration released the first image of this object too, a glowing, flickering ring of light surrounding an absence. Our own galactic center revealed at last. Sagittarius, a star, contains approximately 4 million solar masses. It is, by cosmic standards, a relatively modest supermassive black hole. And yet, if you were to replace our Sun with Sagittarius A star, it would extend roughly to the orbit of Mercury. The scale is almost impossible to hold in the mind for long without it slipping away. Now imagine two objects like this, or larger, much larger. Some galaxies host supermassive black holes containing tens of billions of solar masses. Now imagine a scenario where the galaxies containing these objects are drawn together by gravity over billions of years. Imagine them merging, their stars passing through one another like two vast clouds of dust interpenetrating in slow motion. And at the cores of these two merging galaxies, the two supermassive black holes gradually drawing closer, closer, closer over timescales that dwarf the current age of the universe. This is not science fiction. This is something that happens, that has happened, that is, in all likelihood, happening somewhere in the observable universe right now. To appreciate the journey toward collision, we need to understand something about how these black holes actually find each other. It is not a sudden thing. It does not happen quickly by any standard we might recognize. Galaxy mergers themselves are extraordinarily slow processes, drawn-out gravitational dances that unfold over hundreds of millions to billions of years. When two galaxies begin to merge, their stars do not crash into each other. Galaxies are almost entirely empty space. The distances between individual stars are so immense that even when two galaxies pass through one another, direct stellar collisions are extraordinarily rare. What happens instead is a gravitational reshuffling, a slow, magnificent chaos. Stars are flung into new orbits. Gas clouds collide, compress, and ignite furious bursts of star formation. The shapes of the two galaxies are stretched and warped and twisted over millions of years into new forms: tidal tails, bridges of stars, spiraling arms pulled into long streaming filaments. And at the center of all this, the two supermassive black holes begin their long approach. In the early stages of a galaxy merger, the two black holes are separated by tens of thousands of light years. They can feel each other's gravity, but the journey toward each other is mediated not through direct gravitational attraction alone, but through a process called dynamical friction. As each black hole moves through the dense stellar environment of the merging galaxy, it gravitationally tugs on the stars around it, pulling them slightly out of their paths. This creates a kind of gravitational wake behind the black hole, a trailing density of stars that exerts a gentle but persistent drag. This drag slowly bleeds energy and momentum from the black hole's orbit, causing it to gradually spiral inward. The black hole does not fall straight toward its partner. It spirals, slowly, patient as a geological epoch. This process takes an extraordinarily long time. The initial stages of inspiral, driven by dynamical friction, can take hundreds of millions to even billions of years to bring the two black holes from a separation of tens of thousands of light years down to a separation of just a few light years. And it is at this point that things become interesting in a way that has, historically, puzzled astronomers deeply. Because here, at a separation of roughly a few light years, the mechanism of dynamical friction becomes less efficient. There are simply not enough stars in the right place to continue robbing the binary black hole system of its orbital energy at the required rate. The two black holes form what is called a hard binary. a tightly bound pair, orbiting each other, but seemingly unable to get close enough for the final merger to occur within the age of the universe. This puzzle became known, rather evocatively, as the final parsec problem. A parsec, for reference, is approximately 3.26 light-years, so the final parsec problem refers to this apparent bottleneck that occurs when the two black holes are within a parsec or so of each other, close by cosmic standards and yet apparently stalled. For decades, this was a genuine theoretical difficulty. If the final parsec problem could not be resolved, it would suggest that supermassive black hole mergers either do not complete or complete only under very specific galactic conditions. But scientists have proposed several mechanisms that may allow black hole binaries to continue losing energy and complete their merger. These include the influence of triaxial stellar distributions, galaxies that are not perfectly spherically symmetric and therefore continuously supply fresh stars to interact with the binary. Gas dynamics may also play a crucial role, particularly in galaxies rich in interstellar gas, where the gravitational interaction between the binary and a surrounding gas disk can efficiently drain orbital energy. And then there is the influence of additional black holes. If a third black hole is introduced into the system, perhaps through a subsequent galaxy merger, the three-body gravitational interaction can rapidly expel one black hole while driving the other two together. This is a hypothesis, a theoretical possibility, but one that is actively studied and is consistent with what we observe. The evidence that supermassive black hole mergers do eventually complete comes from multiple directions. We have observed dual-active galactic nuclei, galaxies where two distinct bright cores are visible, corresponding to two actively feeding supermassive black holes orbiting each other at separations of thousands to hundreds of light-years. Some of the most compelling examples come from surveys like those conducted by the Chandra X-ray Observatory and the Hubble Space Telescope, which have identified numerous candidate dual quasars and dual AGN in merging galaxy systems. These are not the final moments of merger, but they are the long middle chapters, evidence that the process is real, that it proceeds, and that nature finds ways to bring these objects together. And then there is gravitational wave astronomy. In September 2015, a pair of detectors in the United States, part of the LIGO collaboration, the Laser Interferometer Gravitational Wave Observatory, registered something that had never been detected before in the history of human civilization. A distortion in space-time, a ripple passing through the Earth, stretching and compressing the distance between two mirrors by an amount smaller than 1/10,000th the diameter of a proton. This signal lasted approximately 2/10ths of a second and was caused by the merger of two stellar mass black holes located roughly 1.3 billion light-years away. It was one of the most remarkable scientific detections in human history, confirming in direct physical terms that gravitational waves, predicted by Albert Einstein's general theory of relativity in 1916, are real, that they travel through space at the speed of light, that they carry information about the most violent events in the universe. But LIGO is sensitive to gravitational waves in a particular frequency range, the kind produced by the merger of stellar mass black holes, objects a few to a few dozen times the mass of the Sun. The gravitational waves produced by merging supermassive black holes, objects millions to billions of times more massive, would vibrate at frequencies far too low for LIGO to detect. These are not ripples in space-time. They are slow, rolling waves, oscillating on timescales of years to decades. Detecting them requires a different kind of instrument entirely. Enter pulsar timing arrays. Pulsars are a particular class of neutron star. the collapsed cores of massive stars that have undergone supernova explosions. Some of them rotate with extraordinary regularity, emitting beams of radio waves that sweep past Earth like a cosmic lighthouse. The most stable pulsars are so precise in their timing that they function as natural clocks, rivaling the accuracy of atomic timekeeping here on Earth. Astronomers around the world have been monitoring arrays of these pulsars. The North American Nanohertz Observatory for Gravitational Waves, or NanoGrav, the European Pulsar Timing Array, the Parkes Pulsar Timing Array in Australia, and others, looking for coherent, correlated deviations in the arrival times of pulsar signals that would indicate the passing of very low-frequency gravitational waves. And in 2023, multiple pulsar timing array collaborations announced something extraordinary. They had found evidence of a gravitational wave background, a faint, pervasive hum of gravitational waves permeating the entire universe, detectable as a correlated signal across dozens of pulsars. This background hum is consistent with what scientists would expect from a cosmic population of supermassive black hole binaries spread across the universe, all in various stages of in-spiral, all generating gravitational waves simultaneously. The universe, it appears, is filled with the vibrations of merging giants. We are, at this very moment, bathed in gravitational waves produced by the slow spiral dances of supermassive black holes in galaxies across the cosmos. This is not science fiction. This is what the data says. It is still being analyzed, still being refined, and the precise origin of this background signal is a subject of active scientific investigation. But the leading interpretation, that it reflects a cosmological population of supermassive black hole binaries, is compelling, and it tells us something profound. It tells us that black hole mergers are not exotic rarities. They are, on the scale of cosmic time and cosmic population, commonplace. The universe regularly produces collisions of unimaginable violence, and it has been doing so for billions of years. Let us return to our two black holes. Let us place ourselves, imaginatively, somewhere near the story. Not in a physical spacecraft. No technology could survive the environment near merging supermassive black holes. But as observers, somewhere far enough away to watch, close enough to appreciate the scale. The two black holes have been circling each other for hundreds of millions of years. The galaxy around them has long since merged into a new elliptical form. Two former spiral galaxies blended into a single, glowing cloud of hundreds of billions of stars. From the outside, this merged galaxy might look relatively calm, its earlier turbulence having quieted over hundreds of millions of years. But at its core, the binary black hole system is entering the final stage of its extraordinary journey. At this point, the two black holes are separated by a distance of perhaps a few hundredths of a parsec, a small fraction of a light year. They are each, let us say, a few hundred million solar masses. Their event horizons are enormous, spanning distances in the tens of millions of kilometers across. Each one is surrounded by a swirling accretion disk, material drawn in from the surrounding galaxy and heated to temperatures of millions of degrees as it spirals inward, glowing brilliantly in X-rays, its light potentially outshining the entire host galaxy if the feeding rate is high enough, a phenomenon known as a quasar. Two quasars orbiting each other, pouring light across the universe as they draw closer to the moment of final merger. The orbital period of this binary at this stage might be years or decades. The two black holes are moving at significant fractions of the speed of light as they circle each other. And now, dynamical friction is no longer the dominant process. Now, the primary mechanism draining energy from their orbit is the very thing that LIGO and pulsar timing arrays detect: gravitational radiation, the emission of gravitational waves. As they orbit each other, the two black holes radiate energy in the form of these space-time ripples, and as they lose energy, they spiral closer. The closer they get, the faster they orbit. The faster they orbit, the more powerfully they radiate gravitational waves. The more powerfully they radiate, the faster they lose energy and spiral inward. It is a runaway process, and it culminates in something the universe has been building toward for 1 billion years. But before we reach that final moment, before we stand at the edge of the greatest collision in the cosmos, we need to understand something deeper. We need to understand what these black holes truly are. Because there is a common misconception, an easy mental shortcut, that treats black holes as simply very massive, very dense objects, balls of matter that have been crushed to extreme densities. And while there is a sense in which this is not entirely wrong, it misses something fundamental about what a black hole actually is. A black hole is not, in the first instance, a thing. It is a region of space-time. More specifically, it is a region from which nothing, no matter, no light, no information of any kind, can escape to the outside universe. The event horizon, the defining boundary of a black hole, is not a physical surface you could land on or touch. It has no material substance. It is a mathematical boundary, a point of no return, defined entirely by the geometry of space-time in that region. What makes a black hole is not what it is made of, but what the structure of space and time looks like in its vicinity. This is one of the most profound and disorienting implications of general relativity. Albert Einstein's 1915 theory describes gravity not as a force in the traditional sense, not as some invisible hand reaching across space to pull objects together, but as a curvature of space-time itself. Mass curves space-time, and objects moving through that curved space-time follow what are called geodesics, the straightest possible paths through a curved geometry. What we perceive as gravitational attraction is simply the natural tendency of objects to follow these geodesics through curved space-time. The moon does not fall toward the Earth because the Earth is pulling it. The moon travels in what is, from its own perspective, the straightest possible path through the curved space-time geometry that the Earth's mass creates. Its path just happens to loop around the Earth when viewed from the outside. Near a black hole, space-time is curved so extremely that all possible paths, every geodesic, eventually lead inward. Once you cross the event horizon, there is no direction in space, no orientation you could point your rocket, no amount of energy you could apply that would let you escape. This is not because of some extreme force being exerted on you. It is because inside the event horizon, the direction of increasing time and the direction toward the singularity have, in a deep mathematical sense, become the same direction. Just as you cannot choose to stop moving forward through time out here in ordinary space-time, inside a black hole, you cannot choose to stop moving toward the singularity. It is the inevitable direction of your future. This is worth sitting with for a moment, because it is genuinely strange and genuinely true according to our best current understanding of physics. Inside a black hole, the future is inward. Time itself pulls you toward the center. There is no escape, not because anything is holding you back, but because there is no future trajectory that leads outward. The singularity at the center of a black hole, or what our equations predict, lies at the center, is where general relativity breaks down entirely. It is where the density becomes infinite, where curvature becomes infinite, where the mathematical framework of general relativity stops producing meaningful answers. Most physicists believe that this breakdown signals not a literal physical infinity, but the limits of the theory itself. A full quantum theory of gravity, which we do not yet have, despite decades of effort, would presumably describe what actually happens in the deep interior of a black hole without producing these infinities. The singularity in this view is a placeholder, a reminder of what we do not yet understand, a door that remains locked, waiting for the physics of the future. And as we contemplate two such objects approaching each other, it is worth holding in mind what an extraordinary thing this truly is. Two regions of space-time, each one representing a place where our deepest physical theories break down, each one containing a singularity that no current science can fully describe, spiraling together across the heart of a billion-star galaxy, radiating ripples through the very fabric of space and time, building toward a moment of unification that will release more energy than any other process in the known universe. The universe has its dramas. This is perhaps the grandest of them all, and it is happening right now, somewhere out there. And it has happened many times before, in many galaxies, at many points in cosmic history. Every large elliptical galaxy, those great, featureless, golden ellipses of ancient stars that populate galaxy clusters throughout the universe, is believed to carry within it the legacy of one or more major galaxy mergers. And each of those mergers almost certainly brought two or more supermassive black holes together on the long road toward collision. The supermassive black hole at the center of every large elliptical galaxy may well be the product of multiple black hole mergers, grown fat over cosmic time through the accumulation of smaller black holes combined in a lineage of titanic collisions stretching back billions of years. Let us consider one of the most dramatic examples of a system that may be in the process of building toward such a collision. The galaxy OJ-287, located approximately 3.5 billion light-years from Earth in the constellation Cancer, is believed to harbor a binary black hole system, one of the most massive and most well-studied candidates known to science. The primary black hole in this system is estimated to contain roughly 18 billion solar masses, making it one of the most massive known black holes in the observable universe. The secondary black hole is estimated at around 150 million solar masses, smaller but still enormously massive by any ordinary standard. These two black holes are believed to orbit each other on a period of roughly 12 years, and the system has been observed to produce periodic optical outbursts, dramatic brightenings visible from billions of light-years away, as the secondary black hole plunges through the accretion disk of the primary twice per orbit. This is not theoretical. These outbursts have been observed and documented over more than a century of astronomical records. The Blazer OJ-287 has been photographed on photographic plates dating back to 1888, and the periodic brightening pattern is visible in archival data stretching back over 100 years. This is a binary black hole system we are watching in real time, catching it in the long, slow middle chapter of its in-spiral. The final merger of this system, when it eventually occurs, will be an event of almost incomprehensible violence, and the gravitational waves it produces will likely be detectable by future space-based gravitational wave observatories. One such planned observatory is LISA, the Laser Interferometer Space Antenna, a mission being developed by the European Space Agency with contributions from NASA. LISA will consist of 3 spacecraft arranged in an equilateral triangle formation, separated by distances of roughly 2.5 million kilometers. flying in a heliocentric orbit trailing behind the Earth. By measuring the tiny variations in the laser light traveling between these spacecraft, LISA will be sensitive to gravitational waves in the millihertz frequency range, precisely the frequencies produced by merging supermassive black holes. When LISA becomes operational, expected in the 2030s, it may open an entirely new observational window on the universe, allowing us to detect and study the final in-spiral and merger of supermassive black holes across cosmic distances, watching in real time as the universe's most powerful events unfold. The anticipation in the scientific community around LISA is immense. It represents not just a new telescope or instrument, but a new sense. Gravitational wave astronomy gives us the ability to perceive the universe in a way that no optical telescope, no radio dish, no X-ray satellite can. We have, over centuries of astronomy, learned to see the universe in light. LIGO and its successors have taught us to hear its vibrations. LISA will allow us to listen to its deepest, slowest rhythms, the rumbling bass notes of supermassive black hole mergers, the undertone of the cosmos. Let us now slow down. Let us focus on the approach, on the final hundreds of thousands of years, an eye blink in cosmic time, before two supermassive black holes finally reach the point of merger. Imagine you are watching from a vast distance, perhaps from a galaxy tens of millions of light-years away. The merged galaxy hosting our binary is a broad, glowing ellipse. At its center, there is a source of light, two sources, close together now, that flicker and blaze as in falling material cascades toward each of the black holes. Sometimes one dominates, flaring brilliantly, sometimes the other. The two accretion disks are not static. As the black holes draw closer, gravitational interactions between the two systems become increasingly violent. Material is flung out of stable orbits. Gas that was slowly spiraling inward is suddenly perturbed, sent on new trajectories, some of it falling faster toward one black hole or the other, causing brief but extraordinary bursts of brightness. If there are jets, powerful, relativistic jets of material launched perpendicular to the accretion disk by magnetic forces near the black hole. These too become unstable and chaotic, changing direction as the black hole's spin axis is perturbed by the growing gravitational influence of its companion. The gravitational field in the center of this galaxy is extraordinary. Space is not flat here. General relativity predicts that massive objects moving at high speeds generate gravitational effects beyond simple Newtonian gravity. They drag space-time around with them in a phenomenon called frame dragging, the lens-thirring effect. A rotating black hole does not just curve space-time, it pulls it around in the direction of its rotation, like a vortex in a fluid. Near the event horizon of a spinning, supermassive black hole, this effect is dramatic. Objects do not simply fall inward. They are also dragged around the rotation axis of the black hole, their trajectories twisted by the rotation of space-time itself. Two spinning black holes in close orbit create a complex, dynamic gravitational environment. The two frame-dragging fields interact with each other. The orbital plane of the binary may precess, tilt and wobble over time, driven by the gravitational interaction between the orbital angular momentum of the binary and the spin angular momenta of the individual black holes. The emitted gravitational waves carry information about all of this: the masses, the spins, the eccentricity of the orbit, the inclination. When future detectors like LISA observe a supermassive black hole merger, they will be able to extract an extraordinarily detailed portrait of the system from the gravitational wave signal alone, mapping out the dynamics of objects that may be too distant and too compact to image directly. The stars of the host galaxy continue to move through all of this in their long orbits. Most of them are entirely unaware, in any meaningful physical sense, of the drama unfolding at the galactic center. They simply continue in their paths, bound to the galaxy by its overall gravitational field. But stars that venture too close to the central binary can be dramatically affected. Some may be slingshot out of the galaxy entirely, flung into intergalactic space at extraordinary velocities by the gravitational interaction with the binary. These are called hypervelocity stars, and we have actually detected such objects in our own galaxy, stars moving so fast that they are escaping the Milky Way, possibly the result of gravitational interactions in our own galactic past. Others may be sent on very tight orbits that bring them dangerously close to one of the black holes, where tidal forces can tear them apart in what astronomers call a tidal disruption event, a brief, brilliant flare of light as the shredded star's material falls into the black hole and is heated to extreme temperatures. The black holes continue to spiral inward. The orbital period grows shorter, days, hours. The gravitational waves being radiated grow stronger, their frequency rising. The two event horizons, each one vast, perhaps tens of millions of kilometers across, are now separated by a distance comparable to their own size. The gravitational field between them is extraordinary. Space-time is deeply curved, twisted, dynamic. The black holes are not rigid objects moving through a static background. They are themselves regions of extreme space-time curvature. And as they approach each other, their gravitational fields merge and interact in ways that are only fully captured by the equations of general relativity, equations that in this regime require powerful supercomputers to solve numerically. The field of numerical relativity, the computational simulation of general relativity in extreme conditions, was developed over decades by physicists who knew that the final moments of black hole merger were too mathematically complex to solve analytically. For years, even decades, despite the power of modern computers, the problem resisted solution. The equations were too nonlinear, the gauge choices too subtle, the numerical methods too unstable. And then, in 2005, a breakthrough. Physicist Franz Pretorius published the first successful numerical simulation of the inspiral and merger of two black holes, following the system through the final orbits, through merger, and through the formation of the final merged black hole and the ringing down of the resulting space-time disturbance. It was a landmark moment in theoretical physics, and it opened the door to a rich program of black hole merger simulations that continues today. These simulations have been essential in providing the theoretical templates that gravitational wave observatories like LIGO use to interpret their detections, comparing the observed signals with libraries of predicted waveforms to identify the properties of the merging objects. So we have the science, we have the observations, we have the theory, the simulations, the gravitational wave detections. And now, at last, let us approach the moment itself, the final orbit, the final seconds. And what happens when two supermassive black holes, each one an abyss of unimaginable gravity, finally merge into one? There is a moment in the final approach of two supermassive black holes when the ordinary language of astronomy begins to fail. Words like orbit and inspiral and approach carry with them an implicit sense of gradual, orderly progression. The image of planets tracing smooth ellipses, of moons gliding serenely around their hosts. But what happens in the final moments before two supermassive black holes merge is something so extreme so geometrically violent, so utterly unlike anything in ordinary human experience, that even the most precise scientific language can only gesture toward it. We are not describing a collision in the way two cars might collide, or even two stars. We are describing the merging of two regions of profoundly warped space-time, two gravitational abysses, two places where the fabric of reality itself is folded so severely that our best physical theories strain and shudder at the edges of their validity. But let us try. Let us slow down time to something our minds can follow, and walk toward the merger step by step. In the final hours before the merger, final hours being a phrase almost comically inadequate given the billions of years of approach that preceded them, the two black holes are separated by a distance roughly comparable to the size of their own event horizons. Let us say each of our black holes has a mass of approximately 500 million solar masses. For a non-rotating black hole of this mass, the Schwarzschild radius, the radius of the event horizon, would be approximately 1.5 billion kilometers. To put that in perspective, the distance from the Sun to Saturn is roughly 1.4 billion kilometers. So each event horizon is a sphere larger than Saturn's orbit around our Sun, and the two of them are separated by a distance of the same order. This is a region of space filled with some of the most extreme conditions the universe is capable of producing, and it is smaller in this moment than our entire solar system. The orbital velocity of the two black holes at this separation is a significant fraction of the speed of light. They are not gently drifting. They are hurtling around each other at relativistic speeds, completing orbits in hours, their gravitational fields interacting so strongly that the very concept of their individual identities as separate objects is beginning to blur. This is one of the most remarkable aspects of the final merger. There is no sharp moment at which you can say, now they are separate, and now they are one. The merger is a continuous process, a topological transition in the structure of space-time that plays out over a finite but brief window of time. From a gravitational wave perspective, this phase of the merger, the last few orbits before the event horizons touch, is called the merger phase, and it represents the peak of gravitational wave emission. The amplitude of the gravitational waves being radiated reaches its maximum. The frequency of the waves is at its highest in the low-frequency band relevant to supermassive black holes, perhaps a wave every few minutes for a system of this mass. And the power being radiated in gravitational waves during this brief window is staggering beyond easy comprehension. Let us try to give it scale. The total power radiated by our Sun, in all forms of electromagnetic radiation across all wavelengths every second of every day, is approximately 3.8 times 10 to the 26th power watts. It is an enormous number. The Sun has been shining at this rate for approximately 4.6 billion years, and will continue to do so for roughly another 5 billion years. It is the engine that drives all life on Earth, the source of essentially all the energy flowing through our biosphere. And yet, during the peak of a supermassive black hole merger, the power radiated in gravitational waves alone can exceed the combined electromagnetic luminosity of every star in the observable universe, simultaneously. Every star, every galaxy, the entire observable cosmos, blazing with the light of hundreds of billions of galaxies, each containing hundreds of billions of stars. All of that light outshone in a single channel of energy emission by the gravitational wave output of two merging black holes. This is not speculation or dramatic exaggeration for effect. This is what the physics of general relativity predicts, and what our numerical simulations confirm. The The gravitational wave luminosity of a merging black hole binary system during its peak can reach values on the order of 10 to the power of 50 watts or more for systems of sufficiently high mass. The observable universe, as an electromagnetic source, radiates somewhere around 10 to the power of 43 to 10 to the power of 44 watts in visible and other light. The difference is enormous, and yet all of this gravitational wave energy passes through ordinary matter, through stars, through planets, through human bodies, with almost no interaction at all. The same property that makes gravitational waves so difficult to detect is what ensures that even this incomprehensible burst of energy causes no direct physical damage to anything it passes through. Space-time ripples. Everything stretches and compresses by an infinitesimal amount, and the universe continues. But let us not move past this point too quickly. Let us stay here, in this extraordinary moment, and think about what it means for space-time itself to be this dynamic. When we describe the emission of gravitational waves, we are describing a process by which energy is carried away from the binary system in the form of propagating distortions of space-time geometry. This is not an abstraction. These distortions are real, measurable, physical. When a gravitational wave passes through you, the distances between every pair of points in your body, and in the room around you, and in the Earth, and in everything else the wave intersects, genuinely change. Not because anything physical is pushing or pulling them, but because the geometry of space itself is oscillating. The metric of space-time, the mathematical structure that defines distances and durations, is wobbling rhythmically at the frequency of the wave. Albert Einstein derived the equations governing gravitational waves from his field equations of general relativity in 1916, just 1 year after the full theory was published. But he was uncertain for years afterward whether gravitational waves were truly physical or simply mathematical artifacts of the coordinate system being used. This uncertainty persisted for decades, and it was not fully resolved until the 1950s and 1960s, when physicists, including Felix Pirani and Hermann Bondi, demonstrated rigorously that gravitational waves carry real energy and can produce measurable physical effects. The subsequent detection by LIGO in 2015 was the definitive experimental confirmation, but the theoretical groundwork had been laid over half a century of careful, sometimes contentious physics. The fact that Einstein doubted the reality of gravitational waves is worth dwelling on. Here was the man who had created general relativity, who had derived the wave solutions from his own equations, who had predicted the bending of light by gravity and the perihelion precession of Mercury with extraordinary accuracy. And even he, looking at his own mathematics, was uncertain whether this particular prediction was telling him something about the universe or something about his choice of coordinates. It is a humbling reminder that even the deepest mathematical insights can be difficult to interpret, that the relationship between equations and physical reality is not always transparent, and that science progresses through a long, collective process of checking and rechecking and questioning, rather than through solitary moments of perfect revelation. Now the two black holes are in their final orbit. The event horizons are close. The gravitational field between them is so extreme that any matter caught in the space between them would be subjected to tidal forces capable of tearing apart not just atoms, but the very structures of space-time geodesics in that region. The accretion disks, which had been glowing brilliantly around each black hole, have been severely disrupted. Some material has been consumed by one black hole or the other. Some has been flung away. Some is swirling chaotically in the space between and around the two event horizons, heated to extraordinary temperatures, radiating brilliantly across the electromagnetic spectrum. An observer in the host galaxy, at a safe distance of tens of thousands of light-years from the center, would see the galactic nucleus blazing with light, the combined output of two feeding, merging quasar-scale black holes, an almost incomprehensibly bright source that could outshine the rest of the galaxy by orders of magnitude. And then, the event horizons touch. This is a precise statement in the language of general relativity. The event horizon is a surface defined by the future light cone structure of space-time, the boundary within which no future-directed causal path can escape to infinity. When two black holes merge, their event horizons first make contact at a single point, and then the contact region expands rapidly as the two horizons fuse into a single, unified surface. This topological change, the merging of two separate surfaces into one, is called the merger proper, and it happens extremely quickly on a timescale comparable to the light crossing time of the system. The time it would take light to cross the combined system, which for two black holes of 500 million solar masses each would be on the order of a few hours. What happens to the singularities? This is a question that general relativity itself cannot fully answer, because the singularity is precisely the place where the theory breaks down. What we can say, based on the mathematical framework of general relativity, is that after the merger, there should be a single, unified singularity inside the new, larger black hole. How the two singularities merge, whether they simply combine, or whether there is some more complex dynamic behavior in the deep interior, is something that our current theories cannot reliably describe. This is one of the genuine frontiers of theoretical physics. It is a place where the unknown begins, and where future theories of quantum gravity will need to provide answers that general relativity cannot. What general relativity does describe well, and what our numerical simulations capture in beautiful detail, is what happens to the event horizon and to the space-time outside the merged black hole in the moments and hours after merger. The newly formed event horizon is not initially a smooth, perfect sphere. It is violently distorted, oscillating, rippling like a drop of water that has just fallen into a still pond. These oscillations are called quasi-normal modes, and they are one of the most fascinating aspects of black hole physics. The merged black hole is ringing, in a gravitational sense, vibrating at specific frequencies determined by its mass and spin, decaying exponentially as energy is radiated away in gravitational waves. This phase of the merger is called ringdown, and it produces a characteristic gravitational wave signal, a rapid damping oscillation at a frequency set by the properties of the final black hole. By observing this ringdown signal, gravitational wave astronomers can, in principle, determine the mass and spin of the newly formed black hole with remarkable precision. More than that, the ringdown signal is a direct test of general relativity's predictions about black holes, specifically the prediction that the quasi-normal mode frequencies depend only on the mass and spin of the black hole and nothing else. This is a consequence of what physicists call the no-hair theorem, the idea that black holes are characterized entirely by just three parameters: mass, electric charge, and angular momentum. Everything else, the detailed history of how the black hole formed, the chemical composition of the matter that fell in, any other complexity, is washed away and invisible to an outside observer. The no-hair theorem is one of the most striking and philosophically provocative results in all of physics. A black hole carries no memory of what it was made from, whether it formed from collapsing hydrogen gas, or from the merger of neutron stars, or from the combination of two smaller black holes. The end result, according to general relativity, is the same: a perfectly smooth, perfectly symmetric, perfectly featureless object described by just 3 numbers. The entire complex history is obliterated. The information that encoded the structure of everything that fell in is, in some deep sense, gone. Or is it? This question, what happens to information when it falls into a black hole, is one of the deepest unsolved problems in theoretical physics, and it sits at the intersection of general relativity and quantum mechanics. According to quantum mechanics, information is never truly destroyed. The laws of quantum physics are time-reversible in a precise mathematical sense. Given the complete quantum state of a system at any moment, you could, in principle, reconstruct the complete state at any previous moment. Nothing is truly lost. It is only scrambled, rearranged, hidden. But if information falls into a black hole and disappears beyond the event horizon, seemingly never to return, this fundamental principle of quantum mechanics would be violated. Stephen Hawking, in a celebrated 1974 paper, showed that black holes are not entirely black. Through a quantum mechanical process now known as Hawking radiation, black holes slowly emit thermal radiation, a faint glow of particles created by quantum fluctuations near the event horizon. Over an extraordinarily long time, for a supermassive black hole, far longer than the current age of the universe, this process would cause the black hole to very slowly lose mass and eventually, in theory, evaporate entirely. But the radiation Hawking described is thermal. It carries no information about what fell into the black hole. If the black hole eventually evaporates completely, and if the radiation it emitted truly carries no information, then the information about everything that ever fell in has been permanently and irreversibly destroyed. This apparent contradiction between general relativity and quantum mechanics is called the black hole information paradox, and it has been argued about, debated, and analyzed by some of the greatest minds in theoretical physics for more than 50 years without a fully satisfying resolution. Various proposed solutions exist, including the idea that information is encoded in the Hawking radiation in extremely subtle correlations that Hawking's original calculation missed, or that it escapes through quantum effects near the end of evaporation, or that it is somehow preserved on the event horizon in a quantum mechanical imprint called a hologram. But none of these proposals has been experimentally confirmed, and several of them lead to their own deep puzzles and paradoxes. The information paradox is not merely an academic puzzle. It touches on something fundamental about the nature of physical reality, about whether the universe is, at its deepest level, fully deterministic and time-reversible, or whether there exist processes that genuinely destroy information and violate this symmetry. The answer, when it comes, will almost certainly require a complete theory of quantum gravity, unifying general relativity and quantum mechanics into a single, coherent framework. This is perhaps the greatest open challenge in theoretical physics today. But let us return to our merged black hole. Let us watch as the ring-down proceeds. The newly formed black hole is spinning. This is almost certain. The orbital angular momentum of the binary, the shared rotation of the two black holes around their common center of mass, must go somewhere when the merger occurs. Most of it is carried away by the gravitational waves emitted during the merger and ring-down. But a significant fraction, typically around 60 to 70% of the maximum possible spin, according to numerical relativity simulations, is retained by the merged black hole as spin angular momentum. The result is what is called a Kerr black hole, a spinning black hole whose geometry is described by the Kerr metric, a solution to Einstein's field equations discovered by Roy Kerr in 1963. A Kerr black hole is more complex and richer in structure than a non-spinning Schwarzschild black hole. It has not one, but two event horizons, an outer and an inner. And outside the outer event horizon, there exists a region called the ergosphere, where space-time is dragged so powerfully in the direction of the black hole's rotation that it is impossible to remain stationary relative to distant stars. Any object in the ergosphere, even light, is carried around the rotation axis of the black hole. The ergosphere is not inside the event horizon. Objects can enter and exit the ergosphere, in principle, and this opens the possibility of a fascinating hypothetical process called the Penrose process, proposed by physicist Roger Penrose in 1969, by which energy could theoretically be extracted from a spinning black hole by an object that enters the ergosphere and splits, with one part falling into the black hole on a negative energy trajectory and the other part escaping with more energy than the original object had. This process, and its quantum field theory analog called superradiance, are fascinating theoretical possibilities. Whether they play any significant role in real astrophysical black hole systems is an area of ongoing research. The ring-down signal decays. The oscillations of the event horizon dampen out. The black hole settles. Within a timescale of, say, tens of hours for a system of this mass, the merged black hole has settled into its final state. A single, spinning Kerr black hole, smooth and stable, larger than either of the two that formed it. The combined mass is less than the sum of the two original masses. Some mass, typically a few percent, has been radiated away as gravitational wave energy during the inspiral, merger, and ring-down. For a supermassive black hole merger of this scale, that few percent can represent tens of millions of solar masses of energy, radiated in gravitational waves over the course of the merger process. This is the most efficient known energy conversion process in the universe, vastly exceeding the efficiency of nuclear fusion, which powers stars by converting only about 0.7% of the mass of hydrogen into energy. Think about that for a moment. Nuclear fusion, the process that powers our sun, that has made life on Earth possible for billions of years, converts less than 1% of mass into energy. A merging black hole system can convert several percent of the total mass of two objects, each containing hundreds of millions of solar masses, into pure gravitational wave energy. The number of joules this represents is so large that there is no meaningful comparison available to ordinary human experience. It is simply beyond the reach of our intuitive number sense. The universe, in those final hours of merger and ring-down, briefly becomes something like a gravitational wave engine of almost divine scale. The host galaxy continues. The stars continue their orbits. Gas that was perturbed by the binary has gradually settled into new configurations. The accretion disk around the merged black hole, once it reforms after the violent disruption of the merger, will power a new phase of quasar activity, material falling into the newly enlarged black hole and radiating brilliantly across the spectrum. This post-merger accretion phase can trigger intense star formation in the host galaxy as powerful jets and winds from the active nucleus interact with the interstellar gas. The energy output from the newly merged supermassive black hole can dramatically reshape the environment of the entire galaxy, heating and expelling gas, quenching or stimulating star formation, sculpting the future evolution of the entire system over hundreds of millions of years to come. This is one of the reasons why supermassive black holes and galaxy evolution are so deeply intertwined. Black holes do not simply sit passively at galactic centers, growing silently larger. They are active participants in the life of their host galaxies, influencing the rate of star formation, the distribution of gas, the chemical enrichment of the interstellar medium. And the merger of two supermassive black holes is, in this sense, also a turning point in the life of a galaxy, a moment that resets the central engine, changes the accretion dynamics, and sets the galaxy on a new evolutionary trajectory. There is something almost biographical about a galaxy in this way. It grows through mergers, acquiring new mass, incorporating new stars and gas. Its central black hole grows too, through accretion and through the mergers of smaller black holes over cosmic time. The galaxy and its central black hole co-evolve. There is even a striking observed correlation between the mass of a galaxy's central supermassive black hole and the properties of the galaxy's stellar bulge, particularly a quantity called the velocity dispersion of stars in the bulge. This relationship, known as the M-sigma relation, was discovered in the late 1990s and early 2000s, and it suggests that the growth of supermassive black holes and the growth of the galaxies surrounding them are not independent processes. They are coupled in some way that is still not entirely understood. The black hole knows how large the galaxy is, or the galaxy knows how large the black hole is, in the sense that these two quantities are not independently free to vary across the cosmic population of galaxies. Something connects them. Something enforces this relationship over the billions of years of galaxy evolution. One widely studied hypothesis involves feedback from the active black hole, the idea that a sufficiently active quasar can drive powerful winds and jets that heat and expel the gas of the host galaxy, shutting off both the gas supply to the black hole and the supply of material for star formation, thereby regulating both processes simultaneously. But the details of how this feedback operates in practice, the precise mechanisms by which black hole energy is deposited into galactic gas on large scales, remain an active area of observational and theoretical study. It is a story still being written in data from observatories around the world and in space. Let us step back now. Let us pull our perspective back from the individual galaxy, the individual merger, and take in a wider view. Across the observable universe, the roughly 93 billion light-year diameter sphere of space that our instruments can, in principle, observe, limited by the age of the universe and the finite speed of light, there are estimated to be somewhere around 2 trillion galaxies, though this number is subject to significant uncertainties and is still a topic of active research. A large fraction of these galaxies harbor supermassive black holes. Galaxy mergers are a fundamental aspect of cosmological structure formation. Large structures in the universe grow through the hierarchical merging of smaller structures, a process that has been operating since the first galaxies formed a few 100 million years after the Big Bang. This means that supermassive black hole mergers are not rare events on the scale of the observable universe. They are part of the machinery of cosmic evolution, happening somewhere in the cosmos throughout the billions of years of the universe's history. When we observe very distant galaxies, looking back in time because of the finite speed of light to when the universe was young, we find evidence of extreme activity. The early universe was populated by quasars, brilliantly luminous active galactic nuclei powered by rapidly accreting supermassive black holes. Some of these early quasars harbor black holes containing billions of solar masses, and they existed when the universe was less than 1 billion years old, less than 7% of its current age. How these black holes grew so massive so quickly is itself a fascinating open question in cosmology. One possibility, explored by theorists, is that they grew through a combination of rapid accretion from massive gas reservoirs in the early universe and through mergers with other black holes. Whatever the mechanism, It suggests that the conditions of the early universe were particularly favorable for rapid black hole growth. As galaxies evolved over cosmic time, merging, forming stars, expelling gas, settling into the large-scale structure of the cosmic web, their central black holes evolved with them. The quasar population peaked when the universe was about 2 to 3 billion years old and has been declining since, as the supply of cold gas available for accretion has diminished. The supermassive black holes at the centers of most large galaxies today, including our own Milky Way's Sagittarius A star, are relatively quiet, accreting at low rates, not currently generating the kind of brilliant quasar emission that characterized the early universe. They are, in a sense, dormant, resting between episodes of activity, their potential for brilliance unrealized in the current quiet epoch of cosmic history. But the mergers continue. Even now, in the current universe, galaxy mergers are ongoing. The Milky Way itself is predicted to undergo a major merger with our nearest large galactic neighbor, the Andromeda Galaxy, in approximately 4 to 5 billion years. This prediction is based on careful measurements of Andromeda's proper motion, its motion across the sky, combined with radial velocity measurements and gravitational modeling. The merger is not guaranteed to be a head-on collision. The trajectories suggest it may be somewhat off-center, with the two galaxies potentially passing through each other once or twice before finally merging into a single elliptical galaxy, a future galaxy that some astronomers have playfully nicknamed Milkomeda. And when that merger occurs, the two supermassive black holes, Sagittarius A star with its 4 million solar masses and the supermassive black hole at the center of Andromeda, estimated to contain roughly 100 million solar masses, will begin their own long in-spiral. The process we have been describing, this vast, patient, gravitationally driven dance toward merger, will play out again in our own galactic future, billions of years from now. Our distant descendants, should any exist, might observe the resulting gravitational wave burst or the brilliant quasar flare that accompanies the merger of the two galactic nuclei from whatever vantage point they occupy in what will by then be a very different cosmic landscape. There is something quietly profound about this. The same story we have been telling, the same physics, the same process of galaxy merger and black hole in spiral and gravitational wave emission, is not just a story about distant, abstract objects in far-off galaxies. It is the story of our own future. Our own galaxy is on this path. The Milky Way, the home of our solar system, the backdrop of every night sky that every human being who has ever lived has looked up at, is itself participating in the larger cosmic process of hierarchical merging and black hole growth. We are not outside observers of this story. We are characters in it. The universe does not distinguish between us and any other galaxy. The same gravitational choreography, the same physics, the same patient unfolding of structure over cosmic time. It applies everywhere, to everything. And that, in its own way, is as humbling as any individual fact about black hole masses or gravitational wave energies. Let us now turn to something that lives in the space between science and philosophy. A question that has hovered over our entire narrative, sometimes explicit, sometimes implicit. A question about observation, about information, and about the nature of what it means for something to happen in the universe. When two black holes merge billions of light years away and gravitational waves spread out from the event, traveling at the speed of light in all directions, carrying away the record of the collision. Who receives that message? Right now, as you listen to these words, gravitational waves produced by merging black holes in distant galaxies are passing through you. Not metaphorically, literally. The geometry of space in your vicinity is very slightly, almost unmeasurably oscillating, stretched by tiny fractions along one axis and compressed along the perpendicular axis dozens of times per second by gravitational waves from stellar mass black hole mergers in distant corners of the universe, and much lower frequency waves from supermassive black hole in spirals are also present, stretching and compressing the distances between objects on a timescale of months or years. You cannot feel any of this. The amplitudes are so tiny, many orders of magnitude smaller than the diameter of an atomic nucleus, that no biological sensing system, no instrument of ordinary engineering could detect them. It takes the most precise measuring devices ever constructed by human civilization, spread across kilometers, cooled to near absolute zero, isolated from every conceivable source of vibration, to register these signals at all. And yet they are real. They are physical. They are there. There is a strange intimacy in this. The universe's most violent events, the mergers of objects so massive and so extreme that they warp space-time around them into something our intuitions cannot follow, send their messages silently through everything, touching everything, moving through every atom in your body. And we, with our fragile instruments and our patient, careful science, have learned to listen. That we can do this at all seems, in quiet moments, almost miraculous. We are small, brief creatures on a rocky planet, orbiting a modest star in the outer arm of a spiral galaxy. And we can hear the mergers of black holes billions of light years away. We can read the geometry of space-time. We can decode messages written in the curvature of the universe. How did this happen? How did the universe produce, within itself, creatures capable of perceiving it on this scale? These are questions that physics alone cannot answer. They touch on the philosophy of mind, on the nature of consciousness, on the relationship between the universe and the observers within it. Some physicists and philosophers have found deep meaning in the fact that the universe appears to have produced observers who can comprehend it, though they are careful to note that this could reflect selection effects rather than any purpose or design. We see the universe as one that produced us precisely because we are here to see it. Whether any deeper conclusion follows from that is a matter of genuine philosophical debate. But the wonder of it is real, regardless of the philosophical interpretation one places on it. The wonder of a species of beings who evolved on a small planet, who learned to chip flint and grow grain and write stories, and who eventually, after thousands of years of accumulated knowledge and countless wrong turns and corrections and breakthroughs, built instruments sensitive enough to feel the passing of a gravitational wave, to register, in the motion of mirrors separated by 4 kilometers, the stretching of space by a fraction of the diameter of a proton, caused by 2 black holes merging more than 1 billion light-years away. That wonder is genuine, and it is not diminished by explanation. If anything, it deepens. We are, in some sense, the universe examining itself. The same matter that was forged in the cores of stars and scattered by their deaths, that gradually assembled into planets and oceans and forests and nervous systems, has arranged itself in such a way that it can perceive, measure, and contemplate the most extreme processes in the cosmos. The atoms in your brain were, billions of years ago, drifting through the void of space or burning in the cores of stellar giants. Now they are thinking about black holes. This is remarkable. It deserves to be acknowledged. Let us return once more to the science, because there is still much more to explore, and because the science itself carries its own form of wonder. One of the most fascinating aspects of supermassive black hole mergers is what they reveal about the nature of time near extreme gravity. We have spoken about the event horizon, about the singularity, about the dynamic behavior of space-time during the merger. But there is something even more fundamental that we have perhaps understated: the way that gravity affects the flow of time itself. General relativity predicts, and experiment confirms, that time passes more slowly in stronger gravitational fields. This is called gravitational time dilation. It is not an illusion or a perceptual effect. It is a real, measurable, physical difference in the rate at which time elapses. A clock placed near a massive object runs more slowly than an identical clock placed far away. GPS satellites, which orbit at altitudes where gravity is slightly weaker than at Earth's surface, run slightly faster than clocks on the ground, and this effect must be corrected for in the software of GPS receivers, otherwise position errors would accumulate rapidly. The correction is small by everyday standards, but it is real, and it has been measured and confirmed many times. Near a supermassive black hole, gravitational time dilation is not small. Deep in the gravitational well of a black hole, say at a few times the Schwarzschild radius, a clock would run dramatically more slowly than one far away. At the event horizon itself, from the perspective of a distant observer, time appears to stop entirely. An observer watching someone fall toward a black hole would see that person's motion slow asymptotically, their image becoming increasingly redshifted and dimmer, approaching the event horizon but, from the distant observer's perspective, never quite reaching it. The infalling person, from their own perspective, crosses the horizon in finite proper time. They experience no special sensation at the crossing, and time continues normally for them. But the universe outside would appear to them to be proceeding at an accelerating rate, with enormous amounts of external time flowing by as they approach the horizon. This asymmetry in the experience of time near a black hole is one of the most philosophically striking predictions of general relativity. Two observers, one far away and one near the black hole, can have genuinely, physically different experiences of how much time passes between the same two events, not because one is moving faster, but because of the geometry of space-time in different regions of the gravitational field. Time is not universal. It is local. It is shaped by mass and energy, and its rate depends on where you are in the gravitational landscape. Near two merging supermassive black holes, the gravitational landscape is extraordinarily complex and dynamic. The space-time geometry is not static. It is changing rapidly in ways that evolve over the course of the merger. The gravitational time dilation is extreme and varies dramatically from point to point in the region of the merger. Hypothetically, purely as a thought experiment, since no technology could survive these conditions, an observer hovering at a safe distance in the vicinity of the merger would experience time passing very differently from an observer far out in intergalactic space. Minutes for the nearby observer might correspond to hours or days for the distant one, depending on exactly where in the gravitational field they were located, and the gravitational waves radiating outward from the merger carry with them, encoded in their geometry, a record of all this complexity. The dance of two space-time curvatures merging, the ringing of the new black hole as it settles, the distortions and oscillations of the combined gravitational field. Decoding this record, turning the squiggling graph of a gravitational wave signal into a full reconstruction of the merger dynamics, is one of the great technical and scientific challenges of modern gravitational wave astronomy, and it is a challenge that is actively being addressed. We are, in a very real sense, doing archaeology on the universe, reading records of events that occurred billions of light years away, and billions of years in the past, inscribed not in rock or ice, but in the fabric of space-time itself, and carried to us at the speed of light across the vast, dark ocean of the cosmos. The universe is full of messages. Learning to read them is the ongoing work of science. And every new instrument, every new detection, every new confirmed theory is another word deciphered in a language that the cosmos has been speaking since the beginning of time. There is a particular kind of silence that exists between galaxies, not the silence of a quiet room, or the stillness of a forest at night, or even the hush of deep ocean water far below the surface. It is a silence of an entirely different order, a silence so vast, so absolute, so indifferent, that the human mind, when it tries to truly hold it, finds itself slipping at the edges. The intergalactic void is not merely empty in the way that a room might be empty of furniture, it is empty of almost everything. The density of matter in the spaces between galaxy clusters is so low that a cubic meter of intergalactic space contains, on average, perhaps a handful of hydrogen atoms. Just a few lonely protons adrift in an unimaginable darkness, separated from the nearest star by distances measured in millions of light years. And yet through this silence, right now, gravitational waves are moving. The after-echoes of 1,000 collisions, 1,000,000 mergers, the accumulated gravitational history of the observable universe, all traveling outward at the speed of light, threading through the void, passing through galaxies and stars and planets, and people without any of them noticing at all. The universe is speaking in a language of geometry, and we have only just, in the last decade, learned to hear even the faintest whispers of it. We have spent this journey traveling from the first long approach of two supermassive black holes through their billion-year spiral, through the violent final merger and ring-down, through the physics of gravitational waves and the nature of space-time itself. We have touched on the information paradox, on the relationship between black holes and their galaxies, on the extraordinary achievement of gravitational wave astronomy. Now, in these final passages, let us venture further. Let us ask the questions that sit at the boundary of what we know and what we only suspect. The questions that keep physicists awake at night, not with anxiety, but with a kind of electric, restless wonder. What lies beyond the event horizon? We have touched on this before, but let us approach it more carefully now, because it is a question that has been examined from many angles by many brilliant minds, and the honest answer is both fascinating and humbling. General relativity gives us a clear mathematical picture of the interior of a black hole, at least up to the singularity. Inside the event horizon, space-time is structured in such a way that the future is inward. All time-like geodesics, the paths followed by massive objects, lead toward the singularity. There is no future trajectory that leads back out. The interior is causally disconnected from the exterior. Nothing that happens inside the event horizon can influence anything outside it. But this mathematical picture, clean as it is, may not be the full story. In recent decades, particularly following the work of Stephen Hawking on black hole thermodynamics and radiation, and more recently, through insights from string theory and the study of quantum information, physicists have begun to suspect that the interior of a black hole, as described by classical general relativity, is, in a deep sense, incomplete. Not wrong exactly, but missing something important, something that a full quantum theory of gravity would supply. One of the most striking recent developments in this area is the so-called firewall paradox, proposed in 2012 by Ahmed Almheri, Donald Marolf, Joseph Polchinski, and James Sully, sometimes referred to as the AMPS paradox after their initials. Their argument, roughly speaking, is that three apparently fundamental principles of physics, the equivalence principle of general relativity, the unitarity of quantum mechanics, and the principle that an infalling observer experiences nothing unusual at the event horizon, cannot all simultaneously be true. Something has to give. Either an infalling observer does not have a smooth, uneventful crossing at the event horizon, perhaps encountering a wall of high-energy quanta, a firewall, or quantum mechanics is not fully unitary, or the equivalence principle breaks down at the horizon, or some other assumption in the argument is incorrect. The firewall paradox generated enormous discussion in the theoretical physics community and remains an active area of research. No consensus solution has emerged. This is not a failure of science. It is science doing exactly what it should, identifying deep contradictions, exploring them rigorously, and following the implications wherever they lead, even when the destination is uncomfortable or strange. The fact that we do not yet have a resolution to the firewall paradox is a sign that there is genuinely new physics to be discovered at the intersection of gravity and quantum mechanics, and that the interior of black holes may hold secrets that our current theories are not equipped to reveal. There are other ideas as well. Some researchers have proposed that black hole interiors are connected to other regions of space-time through structures called Einstein-Rosen bridges, or wormholes, theoretical solutions to Einstein's equations that connect distant points in space-time through a kind of geometric shortcut. The original idea of a wormhole was proposed by Einstein and Rosen in 1935, though at the time they did not interpret it in terms of traversable connections between distant regions. More recently, a striking and mathematically deep connection has been explored between entangled pairs of black holes and wormhole geometries, captured in a conjecture sometimes written as ER equals EPR, connecting the Einstein-Rosen bridge to quantum entanglement, as described by the famous Einstein-Podolsky-Rosen thought experiment. This connection between geometry and quantum entanglement is being actively explored as a possible pathway toward understanding how space-time itself might emerge from underlying quantum information. These are hypotheses, theoretical explorations, not established facts, but they represent some of the most creative and rigorous thinking at the frontier of physics today. The broader program of research that all this belongs to, the effort to understand the quantum nature of space-time and gravity, goes under various names and approaches: string theory, loop quantum gravity, causal dynamical triangulation, asymptotic safety. These are some of the frameworks being actively developed. None of them has yet produced a complete, experimentally confirmed theory. The problem is genuinely hard. General relativity and quantum mechanics are both extraordinarily successful in their own domains, but they rest on different mathematical foundations and, in certain extreme situations, make predictions that cannot simultaneously be correct. Finding the deeper framework that encompasses both is arguably the central unsolved problem of fundamental physics. Black holes, and supermassive black hole mergers in particular, are important in this context not just as objects of astronomical study, but as theoretical laboratories. The extreme conditions near and inside a black hole are precisely the conditions where the effects of quantum gravity should be most significant. A complete theory of quantum gravity should make definite predictions about what happens at the singularity, about the fate of information, about the structure of space-time near the event horizon. When we eventually have such a theory, and there is every reason to hope that we will, even if we cannot know when, observations of black holes and their mergers will be among the most important tests of it. The future of gravitational wave astronomy holds extraordinary promise in this regard. LISA, when it flies in the 2030s, will be sensitive to supermassive black hole mergers across vast cosmic distances, potentially detecting mergers at redshifts of 10 or more, corresponding to a time when the universe was less than 500 million years old. These observations will map out the merger history of supermassive black holes across cosmic time, testing models of galaxy formation and evolution, probing the growth of the first black holes in the early universe, and potentially revealing new physics if the observed merger signals deviate from the predictions of general relativity. Beyond LISA, even more ambitious concepts have been proposed. The Einstein Telescope and Cosmic Explorer are planned ground-based gravitational wave detectors that will surpass LIGO in sensitivity by orders of magnitude, potentially detecting the merger of stellar mass black holes throughout virtually the entire observable universe. The combination of space-based and ground-based gravitational wave observatories, together with traditional electromagnetic observations and the emerging field of multi-messenger astronomy, coordinating gravitational wave, electromagnetic, and potentially neutrino observations of the same events, promises to open an era of truly comprehensive cosmic observation, unlike anything we have known before. Multi-messenger astronomy had its coming-of-age moment in 2017, when the merger of two neutron stars was detected simultaneously in gravitational waves by LIGO and Virgo, and in gamma-ray light by the Fermi Space Telescope, followed by detections across the entire electromagnetic spectrum: X-ray, ultraviolet, optical, infrared, and radio, by dozens of observatories around the world. This single event, a neutron star merger called GW170817, confirmed that neutron star mergers are a site of heavy element nucleosynthesis, the process by which elements heavier than iron, including gold and platinum, are forged in the universe. And it also provided an independent measurement of the Hubble constant, the rate of expansion of the universe, using gravitational waves as standard sirens. The scientific return from that single event was extraordinary, and it demonstrated what becomes possible when different channels of cosmic information are combined. For supermassive black hole mergers, the multi-messenger picture will be similarly rich. The gravitational wave signal from LISA will be accompanied potentially by electromagnetic counterparts, the brilliant flaring of accretion disks, the launching of relativistic jets, the X-ray, ultraviolet, and optical emission from perturbed gas falling into the merged black hole. Identifying and studying these counterparts will allow scientists to connect the gravitational wave signal to the astrophysical context of the merger, linking the physics of space-time dynamics to the physics of gas, radiation, and the galactic environment. This is science at its most ambitious and most collaborative, a global, coordinated effort to read the universe in every language it speaks. Let us now consider for a moment the perspective of scale. We have spoken about individual mergers, specific systems, particular galaxies, but let us zoom out further. Let us consider the largest structures in the universe and ask what role supermassive black hole mergers play in the grandest cosmic narrative. The universe is not uniformly distributed. On the largest scales, galaxies are arranged in a cosmic web, a vast, three-dimensional network of filaments and sheets surrounding enormous voids. Galaxy clusters, collections of hundreds to thousands of galaxies bound together by gravity, sit at the intersections of these filaments, the dense nodes of the cosmic web. These clusters are the largest gravitationally bound structures in the universe, containing total masses of hundreds of trillions to quadrillions of solar masses, dominated by dark matter and hot intergalactic gas. And at the centers of the largest galaxy clusters, at the centers of the enormous elliptical galaxies that typically dominate these systems, sit some of the most massive black holes ever measured. The galaxy M87, whose central black hole we have already mentioned, sits at the center of the Virgo cluster, one of the nearest large galaxy clusters to our own Milky Way. The Virgo cluster contains more than 1,300 galaxies and lies roughly 55 million light-years away. Its central black hole, containing 6.5 billion solar masses, is the product of billions of years of hierarchical merging. Countless galaxy mergers, each potentially accompanied by a black hole merger, each event growing the central black hole larger. The M87 black hole is, in this sense, a monument to cosmic history, a record of the accumulated growth over the age of the universe. Even more extreme examples exist. In several of the most massive galaxy clusters in the universe, the central elliptical galaxies, sometimes called brightest cluster galaxies, harbor black holes estimated at tens of billions of solar masses. The galaxy NGC 1277 in the Perseus cluster was at one point estimated to harbor a black hole of up to 17 billion solar masses, though subsequent analyses have suggested somewhat lower values and the precise mass remains uncertain. TON 618, a quasar located approximately 10.4 billion light-years from Earth, harbors a black hole estimated at approximately 66 billion solar masses, one of the most massive black holes known. These extreme objects are outliers, the most massive endpoints of a distribution of black hole masses that spans many orders of magnitude, from the stellar mass black holes produced by individual star deaths through the intermediate mass range of thousands to millions of solar masses, to the supermassive regime of millions to billions, and finally to these ultra-massive behemoths at the peak of the distribution. Understanding how the most massive black holes grew so large is one of the outstanding questions of observational cosmology. The fastest quasars in the early universe, objects existing when the universe was less than 1 billion years old, already contain black holes of 1 billion solar masses or more. Growing a black hole to this mass in less than 1 billion years requires either sustained rapid accretion, the merging of many smaller black holes, the formation of very massive initial seeds, perhaps through the direct collapse of massive gas clouds in the early universe, or some combination of these processes. Each of these scenarios makes different predictions about the properties of the early black hole population that future observations, including LISA, will be able to test. The story of supermassive black holes is, in this sense, inseparable from the story of cosmology itself. The study of the origin, evolution, and large-scale structure of the universe. Black holes are not peripheral characters. They are central actors. Their growth and mergers are woven into the fabric of galaxy formation, into the structure of the cosmic web, into the chemical enrichment of the universe through the elements forged and dispersed in the stellar systems that surround them. And all of this unfolds against the backdrop of an expanding universe. The expansion of the universe, first discovered by Edwin Hubble in the 1920s through observations of the recession velocities of distant galaxies, and found in 1998 to be accelerating, driven by a mysterious quantity called dark energy, adds another layer of context to everything we have discussed. As the universe expands, galaxies that are not gravitationally bound to each other recede. The large-scale structure of the universe is slowly changing. Galaxy clusters, which are gravitationally bound, will eventually isolate themselves as the expansion carries away their more distant neighbors. In the extremely far future, tens of billions of years from now, the universe will look very different from today. Most galaxies will have receded beyond each other's observable horizons. Individual galaxy clusters will become isolated islands in an increasingly empty cosmos. Within these isolated clusters, merging will continue. Galaxies will continue to fall together, merge, grow larger. Supermassive black holes will continue to grow through accretion and merger. But eventually, far in the future, the rate of gas supply and stellar fuel will diminish. Stars will stop forming as the available gas is consumed. The stellar populations of galaxies will age and die, their short-lived bright stars burning out first, leaving behind progressively cooler, dimmer red and brown dwarfs. The universe, on the scale of tens to hundreds of trillions of years, will enter what cosmologists poetically call the degenerate era, a time when the lights of the universe are going out, one by one, and the cosmos becomes increasingly dark and cold. In this far future, the supermassive black holes at galactic centers will be among the last persistent features of the original cosmic structure, surrounded by the cold remnants of dead stars, white dwarfs, neutron stars, black holes. They will continue to slowly grow, accreting whatever material finds its way to their vicinity. And eventually, their host galaxies will themselves begin to dissolve as gravitational interactions over extraordinary timescales fling stars out of the galaxy or send them inward to be consumed by the central black hole. Even the black holes themselves are not eternal. Hawking radiation, that slow quantum leakage of energy from black holes predicted by Stephen Hawking in 1974, will, over immense timescales, cause every black hole to very gradually lose mass and eventually evaporate. The timescale for this process is almost beyond comprehension. A black hole with the mass of our Sun would take approximately 2 × 10 to the 67th power years to evaporate through Hawking radiation, a number so much larger than the current age of the universe that comparing them is almost meaningless. For a supermassive black hole of billions of solar masses, the timescale is incomprehensibly longer still. But in a universe that is potentially infinite in future time, even these unimaginable spans are not insurmountable. Eventually, in principle, even the most massive black holes in the universe will evaporate. What happens in the final moments of black hole evaporation is another of the deep unsolved problems of theoretical physics. As a black hole evaporates, it grows smaller and smaller, its temperature rising as it shrinks. Hawking radiation has the extraordinary property that smaller black holes are hotter than larger ones, the temperature being inversely proportional to the mass. A solar mass black hole, radiating Hawking radiation, would have a temperature of only about 60 nanokelvins, far colder than the cosmic microwave background radiation, which currently fills the universe at a temperature of about 2.7 Kelvin. In the current era, black holes are actually absorbing more energy from the cosmic microwave background than they emit through Hawking radiation, and so they are growing rather than shrinking. Only in the far future, when the universe has cooled sufficiently, will Hawking evaporation begin to dominate. But as a black hole evaporates and approaches the end of its life, the Hawking temperature rises, potentially dramatically, in the final stages. What happens when a black hole has evaporated down to the Planck mass, the smallest meaningful mass scale in quantum gravity, approximately 2.2 × 10 to the -8 kilograms, is genuinely unknown. At this point, quantum gravity effects become dominant, and our current theories offer no reliable guidance. The black hole might evaporate entirely in a final burst of radiation. It might leave behind a stable Planck mass remnant. It might transition into some other form of matter or energy. This is an area where the answers, when they come, will almost certainly require a complete theory of quantum gravity to provide. It is one of the beautiful, strange qualities of physics that the very largest phenomena in the universe, the merging of supermassive black holes, the evolution of galactic structure, the fate of the cosmos, are connected at their deepest level to the very smallest, the quantum behavior of particles, the structure of space-time at the Planck scale, the unresolved tensions between relativity and quantum mechanics. The universe does not separate the large from the small. Gravity, the weakest of the fundamental forces at the level of individual particles, becomes dominant at cosmic scales. Quantum effects, negligible for planets and stars, become central at the moment of black hole formation and the end of black hole evaporation. The universe is one thing, described by one set of physical laws, and understanding it fully requires understanding it at every scale simultaneously. We are far from that complete understanding. We know an enormous amount, far more than any previous generation of humans, and the pace of discovery continues to accelerate. Each new gravitational wave detection teaches us something new about the population of compact objects in the universe. Each new image from the James Webb Space Telescope reveals the early universe in unprecedented detail, showing us the first galaxies and the first active black holes forming in the cosmic dawn. Each new pulsar timing measurement refines our picture of the gravitational wave background. Each new numerical relativity simulation deepens our understanding of the dynamics of merging black holes. The pieces are slowly assembling into a coherent picture, and the picture, even in its incompleteness, is already extraordinary. But let us not lose ourselves entirely in the future of science, as wonderful as that future is. Let us come back, one final time, to the merger itself, to the thing we have been circling throughout this entire journey, the way a planet circles a star, drawn inward, orbit by orbit, to the heart of the story. Two black holes, merging, in the dark. We have described the physics, we have given the numbers, we have explained the gravitational waves, the ring-down, the quasi-normal modes, the no-hair theorem, the information paradox. But there is something in the pure imagery of it, something in the attempt to simply picture it, to hold it in the mind's eye, that deserves its own moment. Imagine being somehow outside the universe, watching, not from any physical location within space-time, but from some impossible vantage point outside the story, able to see the geometry of space itself as a visible thing. You would see, in the region of the merger, space curving, not as a metaphor, but literally the way a rubber sheet curves when a heavy object rests on it, except in 3 dimensions and dynamic, changing moment to moment. Around each black hole, the curvature is extreme, space bending so severely that light rays passing close to the event horizon loop around, orbit, or spiral in. The photon sphere, the region where light can orbit the black hole, glows with a ring of brilliance as light caught in unstable circular orbits briefly illuminates the environment before spiraling in or escaping. As the 2 black holes draw together, their individual photon spheres begin to interact. Light rays passing through the region between them are bent by both gravitational fields simultaneously, creating a complex, caustic pattern of lensing. If there is any gas or dust in the vicinity, and in a merging galaxy there may well be, it would be lit by this extraordinary lens, its image multiplied and distorted and smeared across arcs and rings by the combined gravitational optics of 2 extreme objects passing close together. The visual effect, if you could see it, would be unlike anything in ordinary experience, a baroque, dynamic sculpture of light and darkness constantly shifting as the geometry of space-time evolves. And then the moment of contact, the event horizons touching, the single point of first contact expanding rapidly as the two surfaces fuse into one. In general relativity, this topological transition is captured precisely by the mathematics, by the structure of the null surface that defines the boundary of the black hole region. But in physical, visual terms, it would look like the moment two soap bubbles touch and instantly merge into one. Except that the bubbles here are not surfaces of soap film, but boundaries of causality, regions of no return, and the merger is irreversible and eternal. The new event horizon that forms is immediately larger than either of its parents. It grows rapidly, stabilizing into the smooth, oblate spheroid geometry of a Kerr black hole as the ring-down proceeds. The ringing space-time smooths out, radiating its excess distortion as gravitational waves that race outward in all directions. Somewhere, far away, perhaps billions of light years from the merger, these waves will arrive at a planet circling a distant star. If that planet harbors any beings capable of building sensitive enough instruments, they might detect them. They might know in that moment that something extraordinary happened, long ago and far away, in the heart of another galaxy. They might begin to tell the story of it. The universe is full of stories. Most of them are told in the language of physics, in the grammar of space-time, in the vocabulary of fields and forces and particles. They are told in all directions simultaneously, to anyone and anything capable of receiving them. We are receivers, imperfect ones, limited by the sensitivity of our instruments and the finitude of our minds and the brevity of our lives. But we are nonetheless receivers. We have been listening for centuries, improving our hearing generation by generation, tuning our instruments to new wavelengths and new frequencies, and every time we have expanded our perception. The universe has revealed something that surprised us, something that changed our understanding of what is real and what is possible. The discovery of gravitational waves was one of those moments. It ranks among the greatest achievements of science, not because it was unexpected exactly, but because of what it represents. For all of human history, until September 2015, everything we knew about the universe beyond our solar system had been learned through electromagnetic radiation. Light, in all its forms: visible light, infrared, ultraviolet, radio, X-ray, gamma ray. These are all fundamentally the same phenomenon: oscillating electric and magnetic fields, traveling at the speed of light, interacting with charged particles, and thus with the matter that makes up stars and gas and dust. Electromagnetic radiation is extraordinarily information-rich, but it is blind to anything that does not interact with electromagnetic fields. And there is much in the universe, much of the most extreme and interesting and violent, that does not radiate strongly in electromagnetic waves. Black holes, by definition, do not radiate electromagnetically from their interiors. Their mergers happen in a regime of extreme gravity that produces electromagnetic radiation primarily from surrounding gas, not from the black holes themselves. To see the black holes directly, to witness their merger in its purest form, we needed a different sense. Gravitational waves gave us that sense. They pass through everything. They are generated by mass in motion, and they carry information about the geometry and dynamics of the most extreme objects in the universe. They are a new window on the cosmos, and through that window, we are already seeing things we never could before. Think about what is coming. LISA, flying in the 2030s, detecting supermassive black hole mergers across the history of the universe. Pulsar timing, arrays building up detailed maps of the gravitational wave background. The Einstein telescope and Cosmic Explorer detecting the mergers of stellar mass black holes throughout the entire observable universe. The James Webb Space Telescope and its successors studying the electromagnetic counterparts of these mergers, connecting the gravitational wave physics to the astrophysical environment. Multi-messenger astronomy networks linking all of these observations together in real time, providing coordinated alerts and follow-up across the entire electromagnetic spectrum and beyond. We are on the threshold of an era of gravitational wave astronomy that will transform our understanding of the universe as profoundly as the invention of the optical telescope transformed it in the 17th century. Galileo turned a small glass lens toward the sky and saw moons orbiting Jupiter, phases of Venus, and the cratered surface of the moon. And the worldview that had stood for millennia crumbled and was rebuilt. The gravitational wave observatories of the coming decades will show us merging black holes, the formation of the first supermassive black holes in the early universe, the ringing of space-time around newly formed Kerr black holes, and perhaps, if our theories need to be revised, something entirely unexpected, something we have not yet imagined. Science has a long history of finding exactly that. The unexpected, the thing that does not fit the theory, the signal that should not be there, the anomaly that, when followed carefully and rigorously and without prejudice, leads somewhere no one had thought to look. There is every reason to expect that gravitational wave astronomy will produce its share of surprises. The universe is more inventive than our theories, and as all of this unfolds, as the instruments improve, and the data accumulates, and the theories are refined and revised, the supermassive black holes continue their work. Somewhere, right now, a galaxy merger is proceeding. The two central black holes are drawing closer. The gravitational wave frequency is rising, slowly, toward the frequencies that LISA will someday detect. The merger is not imminent. Imminent has no meaning on these timescales, but it is inevitable. And when it happens, the universe will ring. It will ring with the purest tone the cosmos knows how to produce. A tone not of sound, not of light, but of space-time itself oscillating. A vibration of the very geometry of reality, spreading outward at the speed of light in all directions, touching everything, changing everything it touches by a vanishingly small but real and measurable amount. A tone that carries the record of two black holes, billions of solar masses each, that circled each other for millions of years and finally became one. A tone that says, this happened, this was real, the universe was changed here. That tone is traveling through you, right now. Not this particular merger, perhaps, but 1,000 others. The universe is humming with the echoes of its own history, and we are finally beginning to hear it. There is a concept in physics called the cosmic horizon, the boundary of the observable universe, the distance from which light has had time to reach us since the Big Bang. Everything within this sphere is, in principle, observable. Everything beyond it, and beyond it, presumably, there is much more universe, potentially infinite in extent, is forever hidden from us, not because it does not exist, but because the light from those regions has not had time to reach us in the 13.8 billion years since the universe began. We can never know what lies beyond the cosmic horizon. We can only reason about it, extrapolate from what we see, and wonder. But within the cosmic horizon, within the sphere of the observable universe, there are an estimated 2 trillion galaxies, hundreds of billions of stars in each one. And at the centers of the large ones, black holes. Black holes that have grown through billions of years of accretion and mergers, that have shaped the evolution of their host galaxies that are generating, at this very moment, gravitational waves that are crossing the universe at the speed of light. The observable universe is not a passive backdrop. It is alive with process, with change, with the ongoing unfolding of physical law across scales from the subatomic to the cosmic. We are inside this story. We always have been. Every atom in your body was forged in the nuclear fires of stars that lived and died before our solar system existed. The calcium in your bones was synthesized in the core of a massive star. The iron in your blood was scattered by a supernova explosion billions of years ago. The oxygen you breathe was produced by nuclear burning in stellar interiors and released into the interstellar medium. You are, in the most literal physical sense, made of stardust, made of the universe. And the gravitational waves passing through you right now are a reminder that you are not separate from the cosmos, observing it from the outside. You are part of it, woven into its fabric, carried along in its expansion, subject to its physics and heir to its history. This is perhaps the most important thing that a long, quiet contemplation of the cosmos can give us. Not merely knowledge, though knowledge is extraordinary, but perspective. A sense of our place in the larger story. A recognition that the scale of the universe, rather than diminishing us, contextualizes us. That being small in a large universe is not a tragedy, but a wonder. That our ability to comprehend scales and processes so far beyond our everyday experience is itself one of the most remarkable things the universe has produced. The philosopher Blaise Pascal, writing in the 17th century before the telescope had revealed the true scale of the cosmos, expressed a feeling of terror at the vast, silent spaces of the universe. The eternal silence of these infinite spaces frightens me, he wrote. It is a feeling many people have experienced. Looking up at a clear night sky and suddenly feeling the vertigo of scale. But there is another way to receive that feeling, not as terror, but as awe, as a recognition that the universe is genuinely and profoundly astonishing, and that we, improbably, impermanently, but really, are here to witness it. Two supermassive black holes colliding is not a story about destruction, ultimately. It is not a story about darkness or violence, though it contains both. It is a story about the universe organizing itself over billions of years into structures of extraordinary complexity and power, following the mathematical laws that govern it with perfect, unerring consistency. It is a story about gravity, the most fundamental and universal of forces, the one that shapes the largest structures in the cosmos, doing what gravity does, drawing things together, building structure, shaping the evolution of matter and energy over cosmic time. And it is a story about knowledge, about beings on a small planet who learned, through careful observation and brilliant reasoning and decades of patient work, to detect and understand events happening billions of light years away, events that occurred billions of years before they existed. That knowledge is fragile. The institutions that produce it, the instruments that enable it, the traditions of open inquiry and rigorous verification that validate it, these are things that have to be built and maintained and defended, generation by generation. But the knowledge itself, once gained, is permanent. The detection of gravitational waves by LIGO in 2015 cannot be undetected. The image of the black hole in M87 cannot be unimaged. The laws of general relativity, tested and confirmed and refined over a century of observation and experiment, will not be forgotten. We carry these things forward, we add to them, and in doing so, we extend, in however small a way, the reach of human understanding into the dark, There is something that the universe seems to be inviting us to do, in its way, to look further, to listen more carefully, to ask better questions, to build more sensitive instruments, to think more clearly about the nature of reality. Whether the universe invites anything is, of course, a philosophical question, rather than a scientific one. The universe does not have intentions, but it does have structure, and that structure is amenable to investigation by minds like ours. The fact that mathematics describes physical reality with such extraordinary precision, that the same abstract equations worked out on paper or blackboard correspond to the behavior of matter and energy across the entire observable cosmos, is one of the deepest and most enduring mysteries of all. The physicist Eugene Wigner called it the unreasonable effectiveness of mathematics in the natural sciences. It remains unreasonable, it remains effective, and it remains, at bottom, mysterious. Perhaps this is where we should rest, not at a conclusion. The universe does not offer conclusions, but at a threshold, at the edge of what we know, looking out into what we do not. The merger of two supermassive black holes is, in one sense, a finished story, a thing that happens, that has happened, that is fully described by the equations and well understood in its broad outlines. But in another sense, it is an open door. The gravitational waves it produces carry questions we have not yet learned to ask. The interior of the resulting black hole holds secrets our theories cannot yet read. The connection between the merger event and the full quantum description of gravity remains to be understood. The information paradox remains unresolved. The gravitational wave background is still being mapped and interpreted. Lisa has not yet flown. The story is not over. It has barely begun. Somewhere out there, in the dark between the galaxies, two massive objects are drawing closer. Their event horizons, each one vast beyond easy imagining, are separated now by a distance smaller than our solar system. They have been circling each other since before the Earth existed. They will merge, perhaps in 1,000,000 years, perhaps in 100 million, and when they do, the fabric of space-time will ring with a clarity and power that nothing else in the universe can match. The gravitational waves will spread outward. They will cross the void. They will arrive here, at our pale blue dot, long after we are gone. Or perhaps, if we are lucky, if our civilization endures, and our science continues, and our instruments grow ever more sensitive, while we are still here to listen. And if we are here, we will hear it. We will decode the signal. We will reconstruct, from the oscillations of space-time, the portrait of two black holes that became one. We will add another sentence to the long, astonishing story of what the universe has been doing all this time. In the dark, at scales our ancestors could never have imagined. The universe is old. It is vast. It is stranger and more beautiful than anything we could have invented. And we are here, briefly, with our eyes open and our instruments tuned, doing our small, extraordinary best to understand it. Somewhere beyond the edge of what we can see, the universe continues expanding into the unknown. The great black holes of ancient galaxies drift deeper into the quiet dark, growing slowly, waiting with infinite patience for whatever comes next. The gravitational waves of 1,000 mergers move through the cosmos at the speed of light, touching everything, carrying the record of everything, the universe's own memory of itself, written in the geometry of space and time. And here, on this small planet, in this brief window of cosmic time, we lie still and we listen, and we wonder, and wondering, we reach. If this journey through the deep universe moved something in you, if these long dark spaces and ancient collisions stirred a sense of wonder you want to carry forward, please consider subscribing to this channel. Every listen, every like, every quiet moment you spend with these stories helps this channel continue exploring the cosmos together. The universe has so many more secrets to share, and we will keep following them, wherever they lead, as far as the darkness goes.